welcome. Welcome to my journey from WebDev to medical visualization Rustacean. My name is David Peherstorfer and I'm also known as Critic on GitHub. I'm a mountain lover, so I like to do all kinds of sports in the mountains, like climbing, running, hiking, you name it. I'm living half of the time in Vorarlberg, which is in the west of Austria, and the other half of the time I'm living in Vienna. I'm the father of a son since January, and I'm married. I've been a web developer for 8 years, been doing Drupal in the backend and Next.js in the frontend. And I recently, like 1 month ago, I joined the 3D team at Dedalus Healthcare. We are doing 3D visualizations of CT and MRI scans, and we are using Rust, WebAssembly, and TypeScript for that. But there was a reason for the switch and why I wanted to go to the medical field. As you already know, my son was born in January, and he was born with a congenital heart defect. So he had to get surgery at 1 month, open heart surgery. And he's doing fine now, and we're really happy about that. And I'm amazed what medicine can do, because when I would have had that condition, I would have died. There was nothing you could do. He will have multiple more operations during his lifespan, so about every 5 to 10 years. And my decision to get into the medical field was that I want to do something for him. And the cool thing is that Dedalus Healthcare creates the software for the hospital where my son got his surgery. So it all worked out really, really well. Our journey through this presentation will be the same as my journey. I started with the basics of Rust. We will quickly go through how I studied Rust in general. Then we'll take a look into computer graphics that we need for the medical visualizations. Then I give you a primer of medical visualizations, and especially the DICOM file type or standard. Then I will show you the prototype, the first one that I built, where I read a DICOM file and rendered this using the 3D crate. And next, I wanted to do my own rendering, so I studied about Raycasting and created my own Raycaster using OpenGL. And last but not least, I ported all of this code, or for a proof of concept, to WGPU. So let's do a quick survey. Who of you is working professionally with Rust? Okay, nice, about half. And who of you is working in the computer graphics field? Okay, there's some hands, nice. And who of you is working in the medical field? Okay, also some hands, nice. So, how I got started with Rust, that was about 2 years ago, and I think it was through Reddit probably, and I just found Rust links, and I guess a lot of you know what it is. It provides exercises, and you can create your solutions in Rust for these exercises, and there's running tests on your solution so you know if your approach was correct. And the cool thing is it always references the chapters from the Rust book, which you need to complete the exercises. And I took a break after I finished this, and then I came back and I read the Rust book again, because a lot of the concept didn't really click for me the first time. So I really suggested you read it twice, and that helps a lot. Next, I built some small projects like a calculator on the terminal, and I adapted a little snake game to use the JKL semicolon, because I was learning the Vim motions at the time as well. So I really suggest that you check out some crates. download the examples and adapt the examples. It doesn't matter what you're interested in, but it's a really good way to learn. But at this time, I didn't really know what I should use Rust for. So once I got a reason and an idea that I want to go into the medical field and I want to do medical visualization, so 3D rendering, I started again to do computer graphics. I had some courses at university already. I studied media informatics and we had a computer graphics course and also a small medical visualization course. So the first step that I took was to go to Scratch a Pixel. It's a really great resource if you want to study about computer graphics in general. It goes through the concepts of rasterization, for example, or texturing, and it gives you all the math background also that you need. It's about the theory of computer graphics. Next, I went to learn OpenGL, which is a really good resource. It's a big tutorial. It starts with the classic draw your triangle and goes into texturization, lighting, and so on. It's made for C++, but you can easily port the code from C++ and use the OpenGL bindings in Rust as well. You could also start with learn WGPU. WGPU is an implementation of the WebGPU standard, and you can use different backends. So you can use OpenGL as a backend, you can use Metal, Vulkan, DirectX 12, and it has this unified API, which is really nice. It's newer than OpenGL, but it's definitely worth a look. Then I found the 3D crate, which comes with the 3D asset crate, and I was really intrigued by the volume rendering example that this crate provides. So it looks like this. This is not actually medical data, but it's only a volume that it's rendering. And I continued with this example. So I changed this example, which we will see in a second. The next thing I did was to read about medical visualization. So this Visual Computing for Medicine is a great book. It's quite big, but it teaches you like how X-rays work, how CTs and MRI scans work. And I realized that I would need to learn how Raycasting is working, because that is used for volume rendering. I also learned that I need to use the DICOM file standard. DICOM is basically this international standard for medical data. It's digital imaging and communication in medicine. It's used in almost all the devices that are out there, especially in radiology and cardiology imaging devices. And it contains a lot of different tags. These tags contain patient data. You can put annotations that a doctor puts on an X-ray scan into the DICOM file. So this is a really huge standard. But I figured out that the image that I need, the frame from a CT, is actually in the pixel data tag. And one CT scan consists of multiple DICOM files, which each have one frame. So it's like an X-ray, but multidimensional. Inside this frame, you have the values in Hounsfield values. These represent the radio density of the material that is scanned. So X-ray or CT scans, you send rays through your body, and it captures the density of the material that it is. There's also a really good crate, which is called DICOM RS. You can use this to read DICOM files and also parse them, and you get then the DICOM tags as an object, so it's easier to handle. So as I already mentioned, my first idea was then to use this 3D volume rendering example and render a DICOM file. For this, I had to load, I think back then the example consisted of 295 frames. I had to load all of them, put them into an array, and then pass this to the 3D volume renderer. And the result looked like this. I was already really happy with it, but then, so that I could see something, but then I wanted to do more. So the next step was to learn about how this rendering works. So I wanted to take the rendering into my own hands. I studied about Raycasting and how I can implement this in OpenGL. So I went back to this Visual Computing for Medicine book, which explains a lot of algorithms that do Raycasting, which is nice. And it also explains what differences there are in sampling the values. I will show how this works in a second. I learned that I needed a maximum intensity protection to make it look better. And this is how Raycasting works. So you have the camera origin, which is basically your eye. You have the screen with the pixels, and then you have the unit cube. Inside this unit cube, you can imagine there would be your volume, and you send a ray from your eye through each pixel of the screen into this unit cube. And if it hits a material in the unit cube, or it starts sampling along this ray inside of the unit cube, and if it hits a material, you take this value, and there are multiple possibilities how you sample. So you can take the maximum value, which is the maximum intensity protection, or you do an average of all the values that you hit in your cube, then you have an average intensity protection in the end. So that was the theory. The next thing was looking for an OpenGL crate. I first used this GL crate for the first prototype to just get the rendering. I think that was also Reddit that pointed me there. I got it to work. I used the Learn OpenGL resource as a basic to build on top of that. And then I tried to adapt a lot of C++ volume renderers. There are a lot of open source GitHub repositories flying around with volume renderers. I didn't get any of them to really run. And I also had no success in really adapting the code to Rust to get it to work. So that was a bit frustrating. But then I found this OpenGL development cookbook, which is also for C++ developers, but I found the code to be easily adaptable into Rust, and it provides multiple volume renderer, which is really nice, but it also goes into different concepts. So you can also probably create your game engine with this book. And now I will show you the result of what I came up in the end with. Okay. Let's run it again. So this is the rendering. You can move the camera here. So this is an example CT scan from the VTK library. You can set here a threshold on the material that you want to see. So I can take away the skin, for example. This is the default shader that came with the OpenGL development cookbook. And I can also switch the shaders to the maximum intensity protection shader. So you can see that the teeth are the most dense part in your body. And then there is also the average intensity projection shader, which makes it a bit transparent. Yeah. And I had some realizations. while implementing all of this. I started out with the GL crate, and I moved to the 3D crate in the end. 3D, as it was also this crate that I used in the beginning, and it provides this high-level volume rendering that you saw, but it also re-exports Glow, which gives you the same OpenGL bindings as GL does. And I moved to 3D because it provides a lot of helpful stuff. For example, this orbit camera, so you have this drag and drop that you can move around your camera, around the volume. And it also provides some data loading for .volume files, which is nice. And it also comes with eGUI, which is a GUI framework. It's also its own crate. And I've used that to create the sliders and also the selection of the shaders. And here you can see the porting of GL to the Glow crate was really easy because it's just OpenGL bindings. And from C++ to Rust, it's similar like this. So stuff is called the same way. There are buffers everywhere. And then there was the bonus challenge, actually. I also wanted to port my renderer to WGPU. It was not that hard, actually, because they have the same concept. There's also buffers, you have your shaders. The shaders are in a bit of a different language, but you can adapt that. There were no major blockers, and I created a small proof of concept, so just to see if the shader, the rendering would work. There are no controls here, so I can't turn around the head, but it works, which is really, really nice. So as a comparison between these things that I used, GL, I wouldn't use that anymore because the last commit was 4 years ago and the maintainer is looking for someone to take over. Glow is really nice because it provides you these low-level bindings for OpenGL, and for the shaders, OpenGL uses the GLSL shader language. 3D is a really cool collection, I would say, of libraries. You have different abstraction layers that you can use for rendering stuff. So you have the Glow re-export, which is the most low-level context, then or abstraction, and then you have a high-level one where you can also just render spheres and cubes and so on. It also provides the eGUI GUI framework, which is really cool, and it uses OpenGL, WebGL, and OpenGL ES, depending on to which target you render. So my code is also working on the browser, which is really cool. And then there's WGPU. As I already mentioned, it's implementation of the WebGPU specification. And you can choose a backend, like Vulkan, DirectX 12, Metal, and so on. And it uses a slightly different shading language, so it uses this WGSL shader language. If you want to reach out, and I highly encourage you, if you're interested in medical topics, in computer graphics, please reach out to me. This is my LinkedIn, and you can check the code here on GitHub. It's open source. If you want to work with us, we have open positions. And you can find the slides here if you want to get all the links. And I want to end with this quote, which became near and dear to my heart. Health is not everything, but without health, everything is nothing. Thank you.